In this series of videos, we will revise Lewis structures and some other introductory topics like oxidation states. These videos are best for first level college or university students, so if you are preparing for E-levels, these videos might help, although the examples that I will be doing are above the scope of E-levels, and my pace will be quite fast. However, no harm in doing examples that are a little bit more exotic. First, we will make sure that you remember how to find octet, formal charge, and oxidation states. The only thing I want you to realize before we start is that all of them, octet, formal charges, or oxidation states, are just tools, abstract concepts used by chemists. Anyhow, to check if an atom has an octet, you count all electrons this atom has in lone pairs and both electrons in each bond that it has. Octet means 8. An atom needs to have 8 electrons around it. So carbon has one lone pair, that is 2 electrons, and 3 bonds, another 6 electrons, a total of 8 electrons. So carbon has octet and is happy, and the same is true for oxygen. Now, to establish an oxidation state, you do a mental exercise of breaking bonds and both electrons from the broken bond go to the atom that is more electronegative. Effectively, we treat all the bonds as ionic, even if that is not true. If we break all 3 bonds in carbon monoxide, the electrons go to oxygen, because oxygen is more electronegative. So oxygen ends up with 8 electrons around it, and carbon with 2. Now we compare that with so-called free atom valence, which simply means number of valence electrons an atom has in the periodic table. So carbon has 4 valence electrons in the periodic table, as it is in the 14th group, and oxygen has 6, because it is in the 16th group. So we can see that carbon has 2 less electrons compared to what it has in the periodic table, so the oxidation state is +2, because carbon is short of 2 electrons. Whereas oxygen has 2 more electrons compared to what it has in the periodic table, so it has oxidation state of -2. The sum of oxidation state of all the atoms in the molecule has to be equal to the charge on the molecule. Carbon monoxide is neutral, so the charge on the molecule is 0. And +2 minus 2 equals 0 indeed. So if you follow what I told you, you shouldn't be surprised that with hydrogen having -1 oxidation state in sodium hydrate. It is because hydrogen is more electronegative than sodium. What if the bonds breaks between atoms of the same kind and therefore of the same electronegativity? Then the bond breaks so-called homolytically, which means that one electron goes to one atom and the other goes to the other atom. Let's take HOO-. So we can see that after we break bonds in the way I just described, both oxygen end up with 7 electrons, which is 1 more compared to what oxygen has in the periodic table. So we got oxidation state of -1 on each oxygen. Hydrogen ends up with no electrons, which is 1 less compared to what it has in the periodic table. So hydrogen has +1 oxidation state. When we sum up all the oxidation states of all the atoms in the molecule, it does give -1, which is the charge on HOO-, and that is how it should be. Notice that this recipe also implies that all the atoms in homonuclear compounds have oxidation of 0. Now, could I explain stuff without using words like homonuclear? Well, yes, but your lecturers will be using them, so you may as well start picking these up. Now, formal charges. It is a little bit like with oxidation states, but you always break bonds homolytically, count the electrons around each atom and compare to the free atom valence. Carbon ends up with 5 electrons, as does oxygen, so carbon has -1 formal charge. Remember, we compare 4 with 5, so carbon has 1 more electron compared to what it has in the periodic table. And oxygen has 1 less electron compared to what it has in the periodic table, so oxygen has +1 formal charge. Here also the sum of formal charges on all atoms must be equal to the charge on the molecule, so we have +1 minus 1 equals 0. So what we just did can be represented by this formula. Unshared number of electrons just means electrons that are not in bonds. And notice that the number of bonds equals to the number of electrons from bonds that break homolytically, because we only take 1 electron from each bond. So the second method is really only a formal way of writing down the first, more graphical method. So let's do another example. Let's do HOO- again. The terminal atom has -1 formal charge, and the rest have the formal charge of 0. So the total charge is -1, which is equal to the total charge on the molecule. Some people call these formal charges, but it would be better just to call it charge, because it is an actual charge on the ion. And by the way, these ions are so-called simple ions, meaning that they are made of 1 atom. So really, to define a formal charge, you need to have a molecule, neutral or charged, with more than one atom. -2 charge on SO4 is also not a formal charge. Again, it's the actual charge on this anion. It is real, if you like. And that's why you cannot store a bottle of SO4 on its own. You need a counterion to balance the -2 charge, like 2 sodium cations or 1 calcium cation 2+. And you know that ions form salts. In an aqueous solution, the salt will be fully dissociated and the cations and anions will be floating about. In a solid state, the salt exists as 3D lattice. Here we see a fragment, precisely a unit cell of calcium sulfate lattice. However, formally, we assign to oxygen from SO4 a -1 charge, and the rest of atoms in SO4 is regarded as neutral. In acetone, all the atoms are neutral, in other words, they carry a formal charge of 0. To reiterate, formal charges are the charges assigned to atoms within a molecule. If a molecule does not carry a charge, that is, if it's neutral, that is telling you two things about formal charges. Either all atoms in the molecule have formal charge of 0, or some atoms do carry a formal charge, but the formal charges cancel out, like in carbon monoxide or nitric acid. In organic chemistry, formal charges are always explicitly drawn on atoms, otherwise the structure would be ambiguous. And the reason why the formal charges have to be drawn is because lone pairs are not drawn in organic textbooks. True, in overwhelming majority of cases, atoms that make up organic molecules obey the octet rule, so you could use octet to calculate the lone pairs. However, in cases where octet is not obeyed, there would be no way to find out the number of unshared electrons on an atom. So, that's why we are using formal charges. As I said, formal charges are always drawn explicitly on atoms in organic compounds. But there is an exception, the nitro group. If you ever forget how nitro group looks like, then you need to recall nitric acid, as the nitro group can be perceived as a derivative of nitric acid, at least formally. Indeed, one of the ways to remember this exception is to think of the nitro group as a derivative of nitric acid, which is inorganic acid, and that should tell you that you need to be careful with formal charges. Indeed, I have been emphasizing many times that formal charges are always drawn on atoms in organic molecules, and you need to be careful with inorganic compounds. In inorganic textbook, you will see compounds with bonding that is often more complicated and versatile, and sometimes formal charges are drawn, sometimes only the total charges are drawn, and sometimes it is not even possible to assign Lewis structures, let alone to assign a formal charge. We will not go into that. We will only discuss some simple inorganic compounds, and most of the examples will be organic. Now it's time for some questions and some additional information about formal charges that I just couldn't fit anywhere. First question is how many lone pairs does sulfur has in this compound? Notice that the dot means there is an unpaired electron on sulfur. That is what we know. The question is, are there any more electrons? If you are still confused, you might use the formula for calculating formal charges, and that is actually the main reason why I introduced it to you. So sulfur has 3 bonds, we break them homolytically, then we add up the unpaired electron, that gives us 4 electrons. We also see that there is no formal charge on sulfur, so there must be 6 electrons around sulfur after we break all the bonds homolytically. That means that 2 electrons are not drawn. So sulfur has 3 bonds, 1 lone pair with 2 electrons that are not drawn, and another lone pair that is so-called half-filled, which means that there is only 1 electron, that is the dot. Now we'll use the equation. As in any equation, you can solve for any term you want. So, we can solve for the number of unshared electrons. Let's call it x plus 1, as we know that there is 1 unshared electron, which is marked as a dot. So, x is 2, which corresponds to a 1 lone pair. I hope you know why chemists pay a lot of attention to lone pairs. When an atom carries a lone pair, then it can act as a base or as a nucleophile, or both. And bases and nucleophiles are at the core of organic chemistry. Now, after this quite challenging question, I got another one. We are using formal charges not only because they allow us to identify the number of unshared electrons. There are two more reasons why chemists use formal charges. Formal charges are necessary to find the best Lewis structure. They also can indicate trends in electrophilicity and nucleophilicity. You don't need to understand this, it's just an overview of what is ahead of us. Thank you for watching, and see you in the next video.